thanks for volunteering. So let's do the first prompt today.
Yeah.
We'll see how far we get, and then we'll we'll
Mhm.
we'll see what we do afterwards. We're gonna try to aim for it's 13:03 right now. We're gonna try to go for about 45 minutes of programming time, and then at the end we'll have time for feedback and
Mhm.
same old stuff. So this problem is gonna be
Mhm.
called
That's good.
graph bar tightness check. Okay, so what we're going to be doing is we're going to be given a graph, and you will return true if and only if the graph
Mm.
is bipartite.
Oh, okay, I see. Check if
Yep.
it's bipartite. Okay, sounds good.
Yep,
And is
that's
that
the
all?
entire prompt. You're free to ask for clarification if you need.
Yeah, sounds good. Sorry, could you clarify on what it actually means
Yeah, so
called
in this
bipartite
case,
again?
so by the way, this is going to be undirected graph, okay? So in this case, our
Mm.
undirected graph is going to be bipartite, if and only if the nodes, so the vertices,
Mhm.
can be partitioned into two sets A and B,
Mhm.
right? Just independent sets A and B, such as every edge
Mhm.
in the graph connects to a node in set A and node in set B.
Oh, every
So
node
every edge in the graph
connects.
connects a node in set A and a node in set B.
Every edge connects. I see. I see. Every edge connects. Okay. Um. Okay. So you say, sorry. Let me just clarify this a little bit. So the nodes. So we're separating the nodes, right? Not the edges itself.
Yeah, so, well, it's not separating just a logical construct. You don't have to actually separate anything, right? It's just that you return true if and
Yeah. Yeah.
only if it is possible
Mm.
to construct two sets A and B, right? And you can put
Two sets
nodes
A and
in
B.
A and
Yeah.
B with no overlap, okay, independent sets A and B. And
Mm-hmm.
after this
Mm-hmm.
construction, it is true if and only if every edge connects a node in A to a node in B, or vice versa. It's undirected, right?
Every edge connects a node in A and in B. Sorry, the only thing I'm a little bit confused right now, when you refer to every edge, do you mean
Yep,
like their original
yep.
set of
The original
edges?
set of edges.
Ah, I see. Every node connects, every edge connects the nodes in A and in B. I see. Um, sorry. So before we actually get into it, I'll just I'm just trying to like clarify, like I just trying to clarify what I actually understand, right? So let's say we have like a graph of like A connects B
Okay.
connects C, for example. So we would separate A and B into itself into a set and C into its own set, right?
So what are
Is
the
that
edges? The edges are A to B and B to C. So in
yeah?
this case, this graph is bipartite because you can put A and C into one set and then B into another set.
Oh,
And therefore, the graph is bipartite because every edge
oh,
connects a
I
node from
see.
set A to set B.
Every edge connect. Oh, the requirement is to connect
Or
from
vice
set
versa.
A
It's,
to set
it's
B, right?
undirected.
Ah, I see, I see, I see. Connect set A to set B. I see. Okay, I see. Um, okay. Sorry, I'm a little bit stumble and
Okay.
um, okay. So, so from so from my initial understanding is that we want to like we want to to paraphrase it in my own
Uh huh.
words essentially is that we try to separate the nodes out such that there's a node in B that connects the node in A to B, right?
Can you say
so
how you put into A and B? Like can you go from the beginning?
um sorry sorry because I don't quite
Okay.
understand it just yet. So so we have so let's say we have A
Okay.
connecting B connecting C, right? So you're saying that we're putting B into one set and A and
Yep.
C into the other set, and we're saying that uh this is bipartite because B connects to A and then B connects to C, right?
It's bipartite because the two edges, which is A, B, and B, C, all the edges fit the following condition. The
Uh,
condition is the edge must connect a node from A to node from B.
I see, I see. Oh, I see. Ah, so in other words, it also means that any nodes that are like neighboring or like adjacent to it cannot be in the same set, right?
Sorry, say it again. I was distracted by the chat. Sorry.
Oh, yeah. So like in other words, um like any nodes are like connect any two nodes that are neighboring to each other, they cannot be the same set.
Yeah,
Is
that is a necessary condition. Yeah, that is true. That is a fact. Yes.
so if I have something like this, for example, I see. Okay, I
Well,
see.
so in this case,
Um,
this case, this is still bipartite, right? Because you can put B into one set and
mm-hmm,
then A, D, and C into another set, and it would still be bipartite,
right.
right? Let me. Do you want
I
me to
see.
give you? Okay. Let
I
me help you
see.
out a little bit. Okay. So let me give you an example here.
Mm-hmm,
That looks something like this.
mm-hmm.
Let's do this. It's okay. It's okay if I just use a drawing board for you. It's a bit easier for me to draw than type out vertical lines.
Yeah, yeah, sure.
Right. So you had
Yeah.
sorry. So you had A, B, and C like this, right? So in this case, we can put
Mm-hmm,
A and C into one group and B into a different group, and now we see the
mm-hmm,
edge one and edge two, right?
mm-hmm.
All these edges fit the condition that it
Yeah,
connects two nodes from different groups, from different sets. Now, if I give you a graph that looks like
I see.
this, uh, let's do A, B, C, D, right? If I do this, these are edges, right?
Mm-hmm,
And then I add an edge over here from A to D. This graph is not bipartite, okay? So maybe it's easier for us to
mm-hmm.
just do this first, okay? Just remove the initial the diagonal edge. Is this graph bipartite?
Um, it is because we could move A and group
Correct,
A and D
correct.
and then B and C, right?
So this is bipartite. Now if I add this
Mm.
edge, is this bipartite now? Okay, and why not?
No, because when we group, yeah, yeah, because if we do the same
Yep.
grouping as before, like A and D, there's an edge exists between the two of them. Ah, I see now. Okay,
Yeah, so for this graph you will return false.
okay. Mm-hmm. I see. Okay, I see I see where it could be failing now. Okay.
Mm-hmm.
If that was the case, hmm, because I'm trying to think of an approach right now of how I should be approaching this. Because if I were to say, if I were to try and generalize it, like if I were to say there, as long as that there are three nodes that have edge exist exist between them, it would fail. But I'm not sure if I could generalize
Sorry,
that
say again. If
just yet.
there's like what's the condition for failing?
As, yeah. So I was saying like, as long as like between the three nodes, as long as like their edges connecting like there are three edges that connecting all three nodes like immediate edges. So like A and D and B and C and B and D. I mean A and D, A and B and B and D. Then I would return false. But I don't think I could generalize that yet. Or at least I'm
Yeah,
not confident that I could
We
generalize
have
it
to be
like that.
careful, right? Because
Yeah.
just that there's a cycle is not a
Hmm.
necessary is not the sufficient condition, right?
Yeah.
What
Yeah.
is
I see.
so what
Yeah. Because
property of three? Because a cycle of three is always not bipartite. Like I hope you notice that,
mm,
right?
That makes sense.
Right. So a cycle of three is not
Mm-hmm.
bipartite. What is the characteristics of a
Mm-hmm.
cycle of three that is not filled by a cycle of four, or vice versa? Because a cycle of four is bipartite, right? As we showed with the ABCD example, right? A cycle of four is bipartite. A
Mm-hmm.
cycle of three, in this case, is not, right?
Is that?
What's the difference?
Mm-hmm. Yeah. Um, there's an edge. Is this between any two pair of nodes?
That is a difference, but that's not
There's any two
exactly the
pair of
condition necessarily. Why don't you draw out an example for cycle of five?
nodes. Mm,
Right? How about you draw a cycle of five and you tell me
yeah.
if that's bipartite?
Yeah. We got A, B, oh, C, D, and D. So if so, like
Yeah.
it's like a normal
So
cycle,
is
right?
this bipartite?
So if I group A and D, C and B, D cannot go anywhere. Or if I group these two, oh, sorry, these two, and E and B. No, I don't think this is bipartite either,
Mm-hmm.
right? Yeah, this is not
Yeah.
bipartite
So
either
right. So
because yeah.
the kind of key property we're looking at here
Mm-hmm.
is known as two colorability. Are you aware of two colorability?
Um,
Okay.
no, I have
Right. So
no, not really.
right.
I think
So
I've
the
heard from
pattern that
that,
we
but
need to
yeah.
notice here is let's just take a subset of three of the graph. So let me get my pen. Where's my pen? Uh, how do I? Oh, it's over here. Yeah. So we just look at, for
Mm-hmm.
example, this subset of the graph, right? If we designate B to be
Mm-hmm.
in set A and A to be, so A must be in set B,
I see.
right? It must be, right? There's no choice. Right now,
Mm-hmm.
A is set B,
Makes
then
sense.
C must be set A. There's no choice, right?
Mm-hmm.
So so
Makes sense.
we can continue this logic. So if C is in set A, then E must be in set B, and then D must be in set A, and B must be set B. But that's a contradiction, right? So the property we're
Mm-hmm.
looking for here specifically is that for all of a graph's neighbors, they must be a different set than your current node. They must be. Yeah.
Sorry, could you repeat
So
the last part?
a graph in this case, in this property we notice is that it can only be bipartite if for a node for all nodes, but let's just say node A for a node, all of its neighbors must be in the other set. They must be, and that property must be true
Right.
for all nodes in the graph.
I see. Oh, I see.
Okay.
Okay.
Yeah.
That makes sense. Mm-hmm. That makes sense. I see. So if I apply that understanding back to like
Yep.
the fourth cycle,
Yep.
so we got A, so we got B and
Yep.
C are neighbors of A, and they let's say we assume them in another graph. D,
Well, D is also a neighbor of A.
oh, I see. It's also neighbor. Okay, I see. Ah, I see. I see. Mm-hmm. That makes a lot more sense now. Okay. Um, if that was the case, okay. So if that was the case, then oh, sorry. Then I think my approach here would just follow like the logic
Okay.
that you've been going through. So like assuming a node, like take given a node, I would just assume
Okay.
its neighbor in the opposite
Okay.
set. And I think my approach here would be like having two different sets and like have two different set. Yeah, have
Okay.
two different sets, and then I would just take a random node, and then I would add all the neighboring nodes to it to the other
Hold on. What
set,
do you mean by take a random node?
and then yeah, like say for example like it's sorry, let me So say for example, right, like let's say I was given like a adjacency list. I could just take like like one of the node, like let's say the first pair of nodes,
Okay.
right? I just take the first
Sure.
node, A for example, and then I would add any neighboring nodes to like its neighboring node to
Okay.
the other set. Like let's say like set two for example, and I would add the current node to set one, and then for the next node, I would double check like is it neighboring node is this in any of the
Yes.
sets? Like essentially, I would check if I could
Yes, that makes
add to
sense.
the other
Okay, no,
set
it's
or not.
fine. It's just you said the word
And then if
random node. I don't want to make sure we're not actually doing random nodes. Okay, no, that's fine. That's fine.
oh yeah 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 okay. So I think I could go with that approach. So like it's somewhat similar to it's somewhat a greedy approach that keeps adding the set. It keeps adding the nodes to two different sets until it
Okay.
cannot do it anymore, and then we return
Okay.
true or false
Yeah,
based
that
on
makes
that.
sense.
Does that make sense so far? Okay, sounds good. And I would assume that the input for the graph would be
Yes, that's fine. Yep.
adjacency list then. Okay. Okay. So yeah, I can just implement this real quick then. So oh, I would say check by part type. So then, so let's say I have a list of edges, and I guess they would be represented as like integer, like they each have their own ID, for example.
Sorry, yeah, what's that?
Hello? Oh, sorry. I would assume that each node is represented by
Yeah,
like
yeah,
a
like a
unique
unique
ID,
number.
right?
That's fine. Yeah, like two
Like
numbers. Yeah.
a number. Okay, sounds good. So, like we mentioned, we could have like two different sets called say set one and set two, for example. And then I'm gonna start iterating through the list of edges. Uh, okay, see. So what can I do here? So given an edge A and B, for example, so what can I do first? Um, Maybe what I can do first is to first check if A is in either set one or two, for example. If it's in neither, then add it. Well, yeah. So I would have to so the node that I'm working with right now, the current node is say node A, and then I would have node B. So I would have to check like if not I guess I would have to check if node B is in either set one or two as well.
Mm-hmm.
Okay, so what can I do here? Um, at each iteration, there's a chance that A and B is already sorted into either sets. Well, I could have like an invariant. Well, yeah. So hmm, let's see. So if I have, so let's say I have A, B, D. So I'm still trying
Okay.
on
Yeah, I'm
the
looking
try
at you.
mode, by the way. So yeah. So if I have A, B, and D, and let's say I encounter D and A and D and B first. So D and A and D and B. That would mean that D would probably in set one, and A and B would probably be in set two. And then when I encounter A and B, what can I do? Um, so first, I would have to first check where A is and where B is, and then I would have to check if they are in the same set. If they are in the same set, then I would have to return false. But if one of them is not in the set, then I can add it to the other set, or I can, yeah. If A isn't, if if neither one is in any set, then I can just randomly add them. Like the A can go in set one, or B can go in set two, for example. Um, sorry, but I'm rambling a bit right now. Um, okay, okay. So yeah, I think I would have to first check if A if they belong to any set. So say for example, um, um, so yeah, sorry. I would have to first grab the nodes first, and then I'm gonna, like I mentioned, I'm gonna check if node A is in either set. So I'm gonna check if um say your set ID, for example, for A would be set. No, that's ah sorry. I don't know why, but I'm
Uh
getting a
huh.
little bit I'm getting a little bit stumbled here. Um okay. So if A doesn't belong to any sets, do I just randomly add it to one of the set right away, or what do I do? That's my main question right now. Same thing for B as
Well,
well.
you can't randomly add it to a set, right?
So
That might not be the correct set.
yeah, yeah, that's true. Well, in um, because my thinking right now, like in a sense that I think I could do that. Uh, because like if say for example, um, if if A is not
Uh
in
huh.
either set, like if A is in not in
Okay.
set one or set two, that means that the node A has never been encountered
Yes.
before, right? So it doesn't really matter if I add to one or add it to two. So that's my notion of like adding to a random set.
Is that
Does
is
that
that
make
true though?
sense? Because
If A has not been encountered, is it actually safe to put it in any random set? Like what? Like why do you think that is safe?
um it's it's safe because like the invariance that the assumption I'm working right now is like at the start of every
Uh huh.
iteration of the loop, uh like my current configurations for the sets are
Okay.
correct. So it's like given yeah, so like because like in the example of A, D, and B, and
Okay.
we have a cycle of three. So D is added to a set, and A and B are added to the other
Right.
sets, right? Like yeah. So up until we see the edge A and B, that configuration is correct because we only saw A and
Yeah.
D and B and B, right? But the moments so if the set say the set C has never been encountered in there, so there's no edge that disprove um there's
Uh
no
huh.
edge that disprove the
Right.
configurations yet.
Right.
That's
So
what I meant.
yeah. So
Yeah.
that I so far agree with, but does that mean that it can be disproved?
Mhm. Sorry, what do you
Okay.
mean?
Let's try this
It
example out.
can
So let's
be.
say I'll draw above your example here.
Mhm,
Right. Let's say we have
mhm,
A, B, C. Just very easy. A, B, C, D. Right. Line. Okay. Let's say
mhm,
the first, and let's
mhm,
say so you have a pair, you have a vector, so you have a list of edges, basically, right? Is like that, like that's your input is a
uh-huh.
list of edges, right? Let's say your list of edges are
Yeah.
ordered such that you see A and B first, and then you see C and D next, okay?
Mhm,
And then the other stuff, and then
mhm,
and then third you see B to C, right? So that we still don't care about that.
yeah.
So first you process A to B,
Yeah.
you assign it randomly, doesn't matter. So let's simply A in group A
Mhm,
and B in group B. It has to be in group B, right?
mhm,
Right. So this is fine. This is correct.
yeah.
Right now you encounter C and D. Okay. So now how do you assign the groups? Tell me how you assign the groups.
Mhm. Um, I would add
But why
C
not
to
C to
A
B and
and
D
D
to
to
A?
B. C to B and D to A. Ah, I see. Yeah, you're right. Mm-hmm. So if we add B, C to B and D to A, then on the next
Yep.
iteration I would fail. I see. I see. Okay, so I was a little bit hasty with my approach. That's for sure. Um, mhm. So what can I do? What can I do in this case
The
then?
easiest thing to do in this case would just be to make a real graph. Make a real graph so that you can traverse
Mm-hmm.
in a predictable order. If your invariant is instead that, well, well, you can have more than one invariant, right? But if you have an invariant such that your edges are always ordered in, for example, DFS order or even BFS order, that would be sufficient for you to never encounter two nodes that are both unseen previously, right? Because this is only an issue if you see two nodes that are both unseen.
Mm, I see. I see. Um, Say, do you mind trying an example for that? Because I'm
Sure.
having a really hard time
Yeah,
seeing it. Yeah.
so the issue here, oh, whoops, that's not the right thing. The issue here that you're encountering is that you don't have the, like, you don't have, oh, where's my pen? Like, uh, your issue is that, is that you don't know how to assign the nodes because both nodes in the edge are unseen, right? If
Mm-hmm.
instead
Yeah.
of, if you were
Yeah.
instead able to construct a graph instead of just having a list of edges, then you would always
Mm-hmm.
be able to guarantee there's both nodes that are always seen in the past. So before
Oh,
solving the bipartite problem, how
I
about
see.
you actually generate a graph
Mm-hmm.
given these edges, such that you can traverse them
I
based on
see.
neighbors and
Okay.
not based on arbitrary pairs of nodes?
I see. I see what you mean. I see what you mean. Um, so just a follow up on that. So what you're proposing right now is that instead of like adding only like assigning only one node at a time to either set, you're saying that I should assign all the neighbors of a node to a set and then this node to the other set, right? Like to make sure that I see all
Yeah,
the
so,
nodes
well,
first.
so that is one way to do it, but the less strong implication is that if you have a graph structure, then instead of just
Mm-hmm.
a list of pair of edges, then what you would be able to do is start at an arbitrary node which you can designate the root, doesn't matter, and then from there you
Mm-hmm.
would arbitrarily designate the roots set, right? Because without loss of generality, you can, like, the root set could be anywhere, it doesn't matter, right? So with a loss of generality, you can set the root
Mm-hmm.
to be
Yeah.
A, and then all the neighbors must be B,
Mm-hmm.
and then you can perform a
Mm-hmm.
traversal from there. And if you traverse given the
Mm-hmm.
neighbors, right, by definition, then the one of the nodes of the pair must be already in a set. So you would never encounter the situation where both nodes
I
are
see.
not known.
Ah, I see. I see what you mean. Okay. Um. Okay. I see what you mean. Okay. If that's the case, then like you mentioned, we can construct a graph first. Then, um, what I can do is a hash map to to map a
Okay.
node with its neighbor, and the construction of the graph should be pretty simple. What I could do is that for every edge that I encounter, I would add um I would add the I would add its pair
Yep.
to its neighbor. So I would add yeah I would add so we have two node first and second. I would add the second node as a neighbor of the first node and vice versa. I'm gonna do that um for the second node as well because it's a
Yep. Yep.
undirectional graph, right? So yeah, that should that should give us a graph. And then what we could do is next is like you mentioned, we could yeah like you mentioned, we could traverse the graphs such that like no pairs are unseen. Okay, yeah. So given a root, okay, I see. But on the first iteration, the roots would be
Yes,
unseen, right?
the very first node you check will
Uh,
be unseen, but that one you can assign arbitrarily because without
mhm.
loss of generation or generalization, it can be either A or B. That doesn't matter, right? So the very first node you can
That
arbitrarily
makes sense.
assign.
I see, I see. Okay, that makes sense. So I guess then we can have like uh a uh, we can have a deficit traversal and then do the checking for the two sets at the same time. So what I mean by that is I'm gonna start create two sets. Let's say set one, set two, for example. I'm gonna pick a random node. Um, yeah, I'm gonna pick a random node to start it as root. And how do I do that? How do I do that? Yeah, maybe I just do graph first, for example. And I'll take the first one. Uh, if I, sorry, graph begin, and I'll grab the first one. So this should give me a random node, any node. So I'll just think of this
Okay.
as the root node, for example, and then I can start traversing it. Um, root uh DFS, for example. Um, since we could since we could add the root node to anything, to any of the set, I'll just add it to set one, for example.
Mm-hmm.
Okay, so now what can we do? So we're gonna be traversing the node. So let's see, this is a node and this is the map. It's where? I mean the graph.
Okay.
And uh we're gonna have the two sets that we're working with. Set one and uh set two, for example. Okay. Um, we should probably have a visited as well, but okay. So I guess like at every level, like at every node, I would add the the current node to set one first, assuming that I haven't seen it, and then I'll add all of its children to set two. Does that sound
You're
correct
gonna
so
add
far?
all of its children to set two. Okay. And you're gonna add the current node to set one.
Well, yeah,
Why would you add it to set
yeah.
one and not set two?
Um,
I'll put it this way, right? If you start your
mhm,
DFS with the root is already in
mhm,
set one, right?
yeah,
And so you know that this node is in
mhm,
set one already, right? So you don't need to touch
yeah,
this node set. It's already added to a set. And in fact,
mhm,
because you're given set one and set two in this DFS, you should be able to determine what set this node currently is in. And
mhm,
per iteration, you can add it. You can add the children or the neighbors rather to the other set. So in other
mhm,
words, in your DFS function, the
yeah.
first parameter will always already be in a set.
I see. Oh, and then I would check. which set it belongs to and add
Yep.
all the children to the other set. I see. I see. I see. Ah, I see what you mean now. So check which node it belongs to. Okay. Okay, I see what you mean now. So I guess so I guess we would have to check which set it belongs to. So uh say node set for example, and I would check which one it belongs to. So if it's belong to one, uh then then if it belongs to one, sorry, let's try this again. I would have to find the other set to add it. So so if set one has the current node, then I would give it set two. Oh, sorry. Then I would give it set two, but if not, I would give it set one
Okay.
instead. Yeah. That makes sense. And now I'm gonna iterate through. I'm gonna go through the list of children. So I'm gonna do child graph node, for example. So if child, so if set one is in um, so set one, that's fine. If it's if set one has the child node, uh, then I will just return false, right? I guess it's down. Yeah, then I would just return false. If not, I would just keep adding it to um. If not, then I would just keep adding it uh
Okay.
to the other set. Yeah.
But you're saying set
If
one
not, I
dot
would just
find
keep
child
adding.
return false. Why is it not set two dot find child?
Ah, yeah. Um. Yeah. Sorry, I should have done this set, for example. I guess I would have to do the same thing here. Set one and set two. Yeah. So I would have to check the current set that the root set is in, and if it finds the child, then I'll just return false. If not, then I'll insert it to the other set first, and then I would have to do another iteration down here to do the default stage. So so down here I would do, say for example, I would have to go through the list of children again, and then I would first check default search of the children of the child. So I would pass the child. I'll start checking the child, pass in a graph, and set one, set two. So if it's false, then I can just return false because then that means that it cannot be
Mm-hmm.
partitioned. But uh, if it's true, then it just keep then can keep can keep moving, and then I can return false here. I return true here. I would need to do another check, another base case here, uh so that I wouldn't have to go to the same
Mm-hmm.
node over and over again. Um, so let's see if this node is. I'm sure there's a better way to do this, but I could also just pass in another set to see if it's already been visited. So if it's already been visited, then I can just ignore it. Um, then I can just return true. And the reason I think I should return true here is because if it fails, if the condition if it visited once and it fails, I think it's gonna just return false and stop traversing in the
Okay.
first place. So I think I should be able to assume this.
Okay.
Does this yeah, does that function make sense so
Yeah,
far?
that makes sense.
Okay. And then I guess in here, um like in the original function, in the main function, I can just call I can just return whatever the result of traversing give me. So just have root and then the graph, set one, set two, and visited, which I have not made yet. Oh, yeah,
Okay.
yeah, that should be correct.
Anything else that we need to go
Mm-hmm.
over before we go to complexity analysis?
Um, Not
Okay.
that I could think
Let's
of.
go to the complexity then.
Yeah. Mm-hmm.
Time and space. What do you think?
Yeah. We can
Okay.
first go through the space first, because yeah, the space should also indicate the time as well. So for space, I guess it grows in the number of nodes. So however many nodes it is, because yeah. So let's say we have n number of nodes. Uh, let's say we have n number of nodes, then the graph should grow to n number of entries, and the vectors, like in the worst case, like all the nodes are connected to each other. In the worst case, each node has n minus one neighboring node, but that should just be if in the worst case, if each node is connected with all the other nodes, n minus one neighboring nodes. So that's sorry. So that means that n we have
Okay.
n nodes, and then for each node we have n minus one neighboring
Why do
nodes.
we have in minus one neighboring nodes?
Uh, if it's connected to like if all the nodes are
Oh, if it's like a
connected to
fully
each other.
connected graph.
Yeah, but yeah, like a fully connected graph. So
Oh,
I'm
okay. What
thinking
if
of
we
like
assume the
the worst
branching
case
factor is
scenario
b
here.
instead of in minus one? I mean,
Sorry?
like that's definitely a worst case. We don't have to assume that though. I think for now, let's assume that the branching factor, aka the median number of neighbors per node, is b.
Mm-hmm. So I guess that would give us like the size of this graph here would be O of n times b,
Okay.
right? And then
Mm-hmm.
for the set one and set two, the size of set one, uh uh if the graph could be bipartite, so like it doesn't terminate early, the size of set one plus the size of set two should be equal to the size to the number of nodes. So that would give us O of n for size of set one plus set two. Same thing for visited as well. So each node can only be visited once. So and there are n nodes. So it's gonna boil down to O of n space complexity for
Okay.
visited as well. And because of that, it should give us the final space complexity of O of n times b.
Does a
Yeah.
DFS not require extra space?
Do you have any questions over? Um. Oh. Uh. It it does require extra space for the call stack. Yeah, I wasn't accounting for that as well. Usually, when we consider space complexity, do we account for the call
Depends
stack
on
as
the
well?
size of the call stack. That depends on the size of the call stack.
Sorry? I see.
But
So
yes, you would generally account
I
for it
see. I
because
see.
otherwise, because it still requires your memory.
Mm-hmm. I see. Um, if that was the case, then it should like if we really think about the worst case scenario where all the nodes are connected
Hmm.
in a line, for example, then the call stack would also be just as bad as there would be as many call stack as the number of nodes that we traverse to. So then we would have essentially all of n memories for the call stack as well,
Yep, that
if
makes
that
sense.
makes sense. Okay. So I guess yeah, uh in gen in general, we should have an O of n times b, considering depending on how big b
Hmm.
is.
And your time complexity you're saying is O times B as well. Is that what the top one is?
Um,
Hmm.
for the time complexity, um, yeah, it should be about the same because we also going through all the neighboring nodes for each node. So there would be children, and we do that n times. So it should also be O of n times b as well. Yeah.
Is that the sorry? Can you say the last part? Why is it times B?
Yeah, because so we also have um we also have like B like on average, right? Like we also have like
Okay.
B children node for like B neighboring nodes for each node. And since we're visiting each node once, since we're visiting each node once and we're
Yep.
visiting n nodes, that would give us
Okay.
n times B for every single time
Yep.
we visit them. So that should be the space as well. Yeah.
Okay. That sounds good. Okay, let's wrap it up here then. Um,
Hmm.
good problem. Good problem. I think let's start from the top, right? How do you feel about this problem?
Hmm.
What were the challenges that you were facing, and how do you feel like you did?
I I feel like I messed it up really, really badly this time. Like I think I one thing that I realized about myself, I think I did this before as well. It's like when I encounter a problem that's somewhat similar to what I've seen before, and I remember what the answer was. Like I didn't
Hmm.
quite remember what the answer was. Like I start to like panic real bad. Like for example, like for this problem, like checking for bipartite, like I just learned this in class as well. So like it was so in my mind, there was no excuse for me to like mess it up
Hmm.
this badly. So like I like halfway through panicked a lot, and yeah, and it was hard to like reason it through while
Yeah.
panicking.
Yeah. I mean, that's a skill you have to practice, right? Like even when you're in a panic
Hmm.
situation, right? Yeah, I mean, some people, right? If you have that stress, if you know how to deal with that stress, you can push through. But most people, you gotta know how to slow down, right? Slow down, take a breath,
Hmm.
and then recover, right? Otherwise, yeah, you're gonna dig
Hmm.
yourself into a deeper and deeper hole. All right, yeah. So let's go
Hmm.
over this problem then. So, graph bipartite-ness, right? This is a pretty classic, school academic problem. Um, you know, we spent
Hmm.
we spent the first about 17 minutes going over the setup of the problem, right? That's gonna be
Hmm.
that's gonna be the biggest time save in this case, right? I mean, for like
Hmm.
most problems, it's actually okay to spend that long if the problem is more intricate, if it's more precise, if there's some
Hmm.
limitations or whatnot, right? But like you said, right, for a problem like this where
Hmm.
there's no ambiguity, it is a very straightforward definition. It's either you know it or you don't, right? You either
Hmm.
know how bipartiteness is defined or you don't know how it's defined, and it's okay if you don't know how it's defined. But I
Hmm.
would personally expect that even if you don't know how it's defined, but you know how graphs are if you know how to represent graphs, like you know a JNC list, these like whatever it is that however you choose to represent graphs. If you know about these things, I think it's pretty hard to justify spending 17 minutes on the setup, right? So what I would do for you generally is
Yeah.
just go
Uh,
brush up on all of the graph terminologies, right? Go brush up on all of
Yeah.
those, figure out the
That's
definitions of that, and then you can do like a quick toy problem per each terminology, just so you can kind of get a feel for what that is, right?
mm,
Typically
mm-hmm.
speaking, for a problem like,
That
for
was
example, graph bipartite-ness, um, this is actually a rephrasing of a problem that is the equivalent solution, which is checking if a graph has odd cycles. This is one thing I don't think you noticed, but a graph is
oh
bipartite if and only if there are no odd cycles. But regardless, right? So
I
problems
see.
like this are the case that it's a case that even if you don't know, you haven't seen it before, which is fine, right? Most people haven't seen this before. That's okay. You should still be able to quickly figure out what is the property that we're testing for, right? Like in other words, you can almost metagame it a little bit, right? Like think about
Mm,
it this way, right? So we're doing this problem, right? It's a graph problem. We must traverse it, right? That's how
mm-hmm.
it works. So we're gonna traverse it. What are we checking for on a traversal? That's the kind of question you should be thinking of. How do we make
Mm-hmm.
this problem into a conditional traversal, right? That's the main thing. And I think if you
I
think about it
see.
from that perspective, it can help you out in general for these graph problems.
I see. I
Okay,
see.
cool. So, right, so bipartiteness, right? One thing I will also say is that when you're drawing diagrams, um,
Mm-hmm.
start with the easy ones, right? So start with the basic case, like what we did with AB, ABC, etc., right? So the basic cases, right? And in
Mm-hmm.
this case, I had to draw
Mm-hmm.
an example which was not bipartite, right? Some interviewers will take that as a negative signal. In other words, right, like if the
I see.
function is returning a boolean, you have to have one case which is true and one case which is false, right? Like that's just how it works. So
Yeah.
when you think about that way, you should at least
Yeah.
communicate. Okay, I want
Makes
to draw
sense.
the true case first, and then give me a second. I'm going to think about the other case, and then come with the right. Otherwise, the interviewer will be worried
Mm,
because the not like the false case is the more difficult case, right? So be aware that like when you're
mm,
drawing diagrams like this, you should account for the problem that we're actually solving, right? So that's going to be the odd cycle
mm-hmm.
condition. Next thing
Mm-hmm.
about right. So yeah, this one required a couple hints, right? That's fine. Um, but
Mm,
I think you need to be more vocal about which hints are useful, which ones aren't useful, and be vocal in the sense that like if you feel like a hint that was just given is really good, and you want to process it for a bit, you should slow the
mm-hmm.
interviewer down and give you a chance to think about it, right? In this case, the hint given was all
Mm,
the way
I see.
from here's an example of a non-bipartite graph, all the way to me outlining the fact that this is a two colorability problem, which means that you need all
Yeah, that's
adjacent
true.
nodes to be in the other group, right? Once
Mm-hmm.
that is said, that is
I
basically
see.
the entire algorithm, and the rest is just implementation, right? So if you had between any of
Mm-hmm.
those points,
That's
if
true.
you had the initiative or you had a bit of at least intuition to recognize that, you should at least stop the interviewer and give yourself a chance to think about that. Because you
I
have to think
see. I
about it from
see.
the interviewer's perspective. If we're already 17 minutes in and you have not thought of the algorithm, you're gonna
Mm,
fail. Like you're just gonna fail the problem,
yeah.
right? So I have to give you more and more hints
Mm-hmm.
so that we
That's true.
aren't stuck on that.
That's
Okay.
true. That
Any
makes
questions
sense.
about the theory or the algorithm?
Mm-hmm. Um. So for so when you say like this is like I should uh um like I should recognize like the like what we're checking for as we traverse. When you say like this is like a odd number cycle, like um yeah, odd length
Yeah.
cycle, right? So like for that, like when like on an interview, like when I come up with like some intuition as that, like should I like I'm not very confident into immediately say that yeah it's an odd length, like so I need to. So I guess I remember jumping into some kind of some kind of assumptions here, but I knew like part of me understand that
Okay.
I was wrong as well, so I didn't want to go with it. So like, how do you know like do you just like go with your intuition and be like, oh, so that's what you feel like, so do you want to keep going at it, or
I don't know what you're
like do
trying
you
to
know what
say,
I'm
but
trying
what
to
I
say?
can
Like
say
it's
is that yeah,
like
your intuition is
mm,
oftentimes not correct, but that's okay because if you have no other intuition, that's the only thing you can go
mm,
off of, right? So it's not a choice you really have. the way I would phrase it, I would say, oh, I
Ah,
think
that's
this
true.
is a problem that involves odd length cycles, right? But I'm gonna put that aside for a bit and think about this thing. Think about whatever thing else you're thinking about, right? And if that doesn't work out, I'm gonna come back to odd number cycles, and it might
Mm,
not work out, might work out, and you might be okay. If it doesn't work out, you come back to odd number cycles. You can ask, hey, is this the
I
right
see.
path we should be following, etc. Right? Generally speaking, if you've already gone down an incorrect path, the interviewer will be more likely to help you onto the correct path because, well, they got the signal. They knew that your intuition was poor on the first
Mm,
part, but they don't need to test your intuition again, right? They already knew it was wrong the
right.
first time. Like they can help you on this part and test your ability to do, for example, implementation, right? So I would say generally you can be vocal about it and
Mm,
just
I
indicate that you're
see.
not sure, so you'll come back to it in the future.
I see. I see. I see. Okay, that makes sense. And sorry, and another thing that I wanted to ask about, like, it's less about the theory of the problem itself, but like, because I was a little bit afraid of like feeling like the interview uh with
Yeah,
silence, because I remember one of the advice that you gave in general was like I should like talk like think out loud. So like was it was it wrong of me like was what I did wrong? Because like I remember like I ramble on a lot and like it's going
it's a
nowhere as
balance.
well. So like
It's a
I wanted
balance.
to
The way I would phrase it
yeah,
is, if you need time to
okay.
think, just say, I'm gonna think about this for a bit. Give me a moment, right? Otherwise, yeah,
Mm-hmm.
rambling as well is not good. But it's the worst thing is if you don't say
Mm-hmm.
anything for a period and I don't know what you're trying to do. Right? That's the worst. So in terms of the worst is to
Mm,
not say anything. The next worst is to ramble about things that are not correct. And the least worst is to say I need some time to
that's
think, give
true.
me a moment, and then come back.
I see. Okay. Okay. That sounds good. Yeah, that's definitely a skill that I need to
Yeah, it
work
takes
on as well.
practice.
Okay. That makes sense.
Okay, just to wrap this up, then the last
Mm-hmm.
thing I'll say
Thank you
is
so much.
implementation wise, a couple notes. Um, right, first, okay, time
Mm-hmm.
complexity is correct, but you should not be. Worst case is worst case given the situation, not worst case given some arbitrary input in a sense, right? Like, yes, it's possible that a graph is fully
Mm,
connected, but the way you should be thinking about that is that you can
right.
define the connectedness by using the branching factor. So that's okay to use as a variable, right? That's the first thing you should do. The second thing is,
Ah,
what was I going to say? Yeah, the second thing is, yeah, graph generation, that's fine. I think it took a bit too long to actually decide to make a graph. That was the part which you shouldn't have gotten stuck on, to be honest. But, I think that's another practice,
mm-hmm.
another thing you can practice. One more thing is when you have two sets, sets one and set two, whatever the problem is, right? If you have two variables, and they don't really matter, it just
Mm,
matters that there's two of them, right?
mm,
It's oftentimes better
yeah.
to, instead of having logic every cycle to check that, which doesn't add complexity. It doesn't add complexity, but it's not clean, and it can get yourself confused. Is
Mm,
just in the
mm,
parameters itself just to pass in this and other, and then
ah,
in your recursive call just to swap them.
that's true.
Right, this is a pattern that you should recognize
Ah, that's
because
true.
it will save you a lot of code. Otherwise, you
I
can
see.
consider, for
This,
example, bringing the visited call into the DFS check so that you don't even add to the call stack if the visited node is next. That's a optimization you can make.
mm, that makes
And
sense.
what else was there nodes wise?
That makes sense.
The booleans are correct. The booleans people get twisted on, but I think you got those correct, so that's actually pretty good. No, I think that's all. I think that's all the notes.
Mm-hmm.
So a couple notes on implementation for you to improve, but most of the time it's going to be about right getting to the implementation phase.
That makes sense. Okay.
Okay. Any other
Okay, that
questions?
makes sense. No, not for now. Thank you
Yeah.
so much.
No worries. All right.
That
It's
was
great.
really
It's great
helpful.
to do another one with you. Take care.
That's great.
Bye bye.
Thank you.